In this video, we're going to look at the electromagnetic spectrum for GCSE Combined Science. The image that most students will have in their mind is this classic image of a wave that gets more and more bunched up as we go along. So this is commonly used to represent the electromagnetic spectrum, and then we take this image and we divide it into sections. So we're going to start here with radio waves. Then we're going to move on to microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Now, at this point, if you haven't watched the electromagnetic spectrum song, go and watch it. Just type it into YouTube. It's incredibly annoying, but incredibly catchy. And students do remember it, and it's really good for not only the order, which they have to remember, but it's also good for the uses, which they have to remember as well. So in reality, each of these sections is divided into kind of quite large bands, and that is of course important, right? It's not just one wavelength, it's microwaves, it's a whole band. And then when we get to X-rays and gamma rays, they do overlap a bit. And this is important because X-rays come from electron transitions, as does everything else. All of these are emitted when electrons jump between energy levels. But gamma rays come from the nucleus. And this distinguishes gamma rays from X-rays. Now, this is more important in the radiation topic, and I've already made a video on that, but it's always good to remind students the difference. These come from electron transitions, these come from the nucleus. What changes as we go along the spectrum? So there's a couple of things that change. From the picture, we can obviously see that the wavelength decreases. And then the trade-off is if the wavelength decreases, the frequency must increase. Right, why is that? Because the speed of an electromagnetic wave is given by this formula: frequency times wavelength. The speed of light in this case is not given by v, it's given by c, right? Because this is the speed of light. And the speed of light is always the same. Right, it's always a constant, unless we're changing material. If we're changing material, then it will slow down, and this is of course refraction. But it is a speed of light. It is a constant, and students should remember that it's 3 times 10 to the 8 meters per second. So that's 3 followed by 8 zeros. So if the wavelength decreases, then the frequency, of course, must increase to keep the speed of light constant. There's one other thing that changes as we go along here, and that's the energy also increases. Right, and that's important because when we get to sort of ultraviolet onwards, UV, X-rays, and gamma rays, these all have so much energy that they are now ionizing. Right, they now have enough energy to remove electrons from atoms, and this of course makes them dangerous. This is why ultraviolet gives us sunburn. X-rays and gamma rays could increase our risk of cancer if we're exposed to them for too long. Now, the one other thing that is useful just to sort of stretch students with is the explanation of what we mean by an electromagnetic wave. So light, as we know, always travels in straight lines, but it is of course a wave. What is it that's oscillating? So we have two things that are oscillating. We have the electric field. Now this is an invisible field in space that we can't see, but we know is there because charges feel a force. And then we have the magnetic field as well, which again is an invisible field in space, but we know it's there because magnets, things with a north and south pole, attract each other. And an electromagnetic wave is an oscillation of both of these fields. So we've got the E field, and then the magnetic field is given by this symbol B. And these are at right angles to each other. And they oscillate, and the wave goes this way. Now, it's worth showing students this, but they don't really need to know it. At triple, they need to know this probably a little bit more for their understanding, and certainly at A level. But at least it explains why it has this name, electromagnetic. And we can also start to explain to students that even though it's a wave, it travels in a straight line in this direction, all right, because the oscillations are oscillating perpendicular to the direction of motion of the wave, which is, of course, a basic property of a transverse wave that we talked about earlier on. You could even talk about photons, because students probably would have heard this term, which are particles of light. Although it does risk confusing some students, because they'll say, well, if it's a particle, why is it a wave? Why is it moving like this? And the answer is just things behave as both particles and waves, but you just sort of have to accept that. It's hard to explain that, and you may or may not want to go into that with your class. That you could say that the particle itself happens to move in a wave like this, but that's not really the best explanation. The students might accept that, or you could say that the particle causes a wave. This is probably what I like doing. Okay, so if we're in water, right, and you have a particle that's moving through water, as it moves, what happens? There are ripples that spread out. So we can say it's a particle that's causing ripples as it spreads out. But like I said, I wouldn't worry too much about this. All right, we also need to look at uses. So for radio waves, the uses is communication. For microwaves, we have two main uses: phone signals, and when we go slightly higher energy, we have cooking food. So it's important really to stress that there are many sub-bands of microwaves. So, the cooking food might be here, but the phone signals might be here. And then we can really stress to students that it is safe to use a phone and it's not going to cook our brain. Infrared, is often known as heat, because anything that's hot is giving off a lot of infrared. We can get some really great thermal images as a result, and it's really worth spending time showing students these. They absolutely love them. And then it explains things like night vision. It explains things like catching criminals. So looking at the heat signal of a criminal, if they're hiding behind a bush, for example, the infrared will go straight through the bush. Or, catching marijuana farms that are in someone's loft. The heat can be picked up from all the lights and equipment through the roof by police in the helicopter. So lots of uses for this. Visible, they often do ask a use of visible, which is of course just seeing. There's not really much else to say. And then ultraviolet, detecting forged banknotes is a good one. And it's worth looking up pictures of different currencies under UV light. Some of them are really quite beautiful under UV light. A really nice demonstration of the fact that ultraviolet can give us sunburn and that we need sun cream to protect us is if you get your arm and you smear on a line of UV pen. So we've got some UV pens, and then over half of it, if you put sun cream on half of it and leave sun cream off the other half, and then you shine a UV light onto your arm, this bit will be blocked and you won't see anything, but you will see the UV pen here because the sun cream is blocking it. Really nice demonstration. and shows that different materials can absorb or block different parts of the electromagnetic spectrum. Importantly as well, glass blocks UV. Right? You can't get sunburnt through glass. You can also talk about, again, the different parts of the UV spectrum. So we've got UVA, B, and C, and you can link this to bottles of sun cream when they will have both, UVA and B rating to them. X-rays, we of course can use for imaging bones. And it's useful to talk about the safety implications of this, that technicians go outside the room or they'll wear, very thick lead aprons. Not too much else to say. Gamma rays, there's quite a few uses which mainly come up in the radiation topic, but we've got things like sterilizing equipment or food. Right? A lot of food in shops is also sterilized with gamma radiation to make it last longer. Ultraviolet actually can also be used for sterilizing water or equipment. So my hairdressers, I always tell my students, have a UV light that they use to sterilize some of their scissors. Gamma rays can also be used for detecting cracks in pipes. They can also be used for imaging the body as tracers. And they can, of course, be used for treating cancer, and that is radiotherapy. And then the one other thing that you might want to go into in a bit more detail is microwaves and how they cook food. So you can talk about if you have a lump of food, the food will have some water molecules in it. The microwaves come in, the water and fats absorb the microwaves. They start to oscillate. They actually resonate. Let's go into that. And then they heat up. And you can talk about how with microwaves, it's a few centimeters of absorption. And then the heat will transfer to the rest of the food by conduction. So that's a nice link to some of the year 9 energy stuff, that we're heating those few centimeters of food, heat then transfers by conduction. And you can contrast this to, say, cooking a piece of toast under a grill. So under a grill, we are heating it by infrared. So we are only heating now the very top surface, and then anything underneath, the heat will transfer into the rest of the food, for example, the toast, again by conduction. So we've got radiation transfer and then conduction heat transfer. And this is quite nice because you can then contrast the two, where we get heating, but effectively soggy food. If you heat a piece of bread in the microwave, it's going to be soggy. Whereas here we can get caramelization, or we can get burning, because we've got a different process of heating. And then you can also do a really, really nice demonstration of microwaves as well. If you get a piece of cheese or chocolate and you put it in the microwave, but you take out the rotating turntable and then you put it on for sort of 20-30 seconds, you will find there's some patches that are melted in the cheese, and those patches will have melted where the microwave is at its point of maximum and minimum displacement, and then it will not have heated where there is zero displacement. So it won't heat here, won't heat here. What the point of this is you can then measure your melted points on your cheese, and you can measure one wavelength. And then you can use the fact that the speed of light is frequency times wavelength. You can look this up on microwave for this. You can measure this with a ruler, and then you can work out the speed of light. You can work out this huge, huge number from just a microwave and a piece of cheese, and it's really nice demonstration. of one where we can measure something that's ridiculously fast, that it's far too fast to see. And this also then explains why we need a rotating turntable, because we need to turn the food so it goes through all of these hot points and all of the food is heated. We need this bit to go through here as well.